And now we'll see that the determinant of the matrix product AB is equal to the determinant of A times the determinant of B. So this is Theorem 1040. So for A and B, both n by n matrices, the determinant of AB is the determinant of A times the determinant of B. All right, so for the proof of this one, for if we write B as a vector or a list of column vectors, then let's see. So this is B dot comma 1, and then out to B dot comma n. If we look at the matrix product, we find that we can distribute sort of the A across each of the coordinates. And so this is probably something that you've no doubt seen. If we have like A times X equals B, where these are all matrices, then we've got like there's A and there's X and there's B. So we've got A, X, and B. And so when we're looking at the things that go into the computation for what happens in the first column here, we have, so if we're thinking of this as x1, this first column vector right here, that's the only part of X that factors into the computations of that first column, because we're going to be doing, like the first row times this column to get that entry, and then we're going to be doing the second row times the same column to get the next entry, and so on and so forth. And in particular, all this stuff over here to the right, it does not factor in to the computation of what's going on in the first column, right? And so that's what I'm saying is going on with this one as well. So the product, figuring out what happens in the first column, you only need the first column of B to find out what's going on with that one. So, and if we look at what those products look like, so A times B dot comma K, I guess, then this is going to be, well, we're going to run out of room is what's going to happen. Then this is going to be, let's see, so we've got A times, and then I can write that B as the jkth entry. So I'm going to just, writing this in terms of the standard basis, right? So here, these terms right here, these are entries of B, so just numbers. And so then that's a linear combination of basis vectors E, and so I can distribute and say, okay, so then that's the same thing as I can take that scalar multiple bjk out in front of A times ej, right? So let's do the computation. If we look at the determinant of AB, this is going to be the determinant of, and then we've got j equals 1 to n, b j1 times aej all the way out to in the last coordinate we've got the sum j equals 1 to n b jn A EJ. Okay, so that's a way of rewriting the thing that we're trying to take the determinant of. And don't worry, it gets worse. And so now what I can do is I can pull out all of the A times EJs, right? Because I've got this sum of vectors in each slot. So I'm going to use linearity as in the previous theorem that we just did, right? The matrix is linear in each of its things. So I can pull out that linear combination, j equals 1 to n bji, those are the coefficients. And then inside I've got the determinant of, then I've got my AEJ all the way out to, and then I've got that terrible sum. In all of the other coordinates, there's still going to be that sum. And I can pull out each one of these. So now I'm going to actually have to have some subscripts on my indices so that the sums aren't all over the same j, because then that would be a nightmare. So I'll call this j1, and I've got bj1, and I pull out all of the other sums as well from each of these. So I use linearity in each of the other coordinates. And I've got all that business times the determinant of, and then I've got AE so there we go. Okay, so these ones are both by the linearity of the determinant. Okay, so then let's see what we've got. Well, this thing that we have here at the end is just some permutation. It's the determinant of A, but the basis vectors have been permuted so that it's basically the columns have been permuted. So, right, because A times EJ is the jth column of A. So then let's see. So this is, now we're taking the sum here over all permutations. And then we've got B J1 1 through B J N N, and then we have the permutation sigma times det A, and so this is A permuted by some sigma, and then let's see. So then we've got well, then this thing that's left out in front here, that's actually the determinant of B. So that's the determinant of B times the determinant of A. All right, and so then after all that work, we have an easy corollary, and that is that the determinant of AB is equal to the determinant of BA, and the proof for that is basically obvious with the theorem under our belt, because you can just pull either one of those apart into determinant A times determinant B, and it doesn't matter which order you write the latter in, so it can't matter which way you write the arguments inside the determinant either. And then we get Another easy corollary, which is actually really useful, and that is that the determinant of the matrix of T is independent of basis. And so to see that, if we take C to be the matrix for T in the basis of V's, whoops, and we take B to be the matrix of T in the basis of U's, then the determinant of C is going to be the determinant of A inverse BA, where A is the change of basis matrix, right? The matrix for the identity going from one basis to the other. And so this is the determinant of A inverse times the determinant of B times the determinant of A again. And now it doesn't matter. Well, actually, I guess I didn't even need to write that out. But this is more or less the proof of the corollary just above. And then we can put them back together in whatever order we want. So I can have determinant AA inverse times determinant B. And determinant of the identity is just 1. So we're done. So in summary, I guess the general principle is that if two matrices are similar, then they have identical determinants.